Hello, in this lecture we'll answer on two questions. In the first question, we'll find out the radius of this circle that is inscribed by triangle ABC, and in the second question, we'll find out the area of this rectangle ABCD that blocks this circle. Okay, so we'll start with the first question. In the drawing, we have triangle ABC. Angle ABC equals to 60 degrees. Angle ACB equals to 75 degrees. Side BC equals to 2 units. And our mission is to find out the radius of this circle that is inscribed by triangle ABC. We will solve this question in two different methods. So we start with the first method. Here we draw from point C perpendicular on AB. So this angle equals to 90 degrees according to our construction. This angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point C and AB as D. So we will focus on triangle ABD, this triangle. In triangle ABD, we have this angle that is equal to 60 degrees plus this angle that is equal to 90 degrees plus this angle that is missing. So we will define it as angle X. In total, the sum of those three angles must be equal to 180 degrees, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So here the sum of the angles in triangle ABD must be equal to 180 degrees. So 60 degrees plus 90 degrees plus X must be equal to 180 degrees. 60 degrees plus 90 degrees is 150 degrees plus X. In total, the sum of those three angles must be equal to 180 degrees. So here we'll subtract 150 degrees from this equation, and we get that X equals to 180 degrees minus 150 degrees. It is equal to 30 degrees. Okay, so here this angle X equals to 30 degrees. We continue to focus on triangle ABD. In triangle ABD, we know that cosine 30 degrees is equal to cosine sine 30 degrees is equal to BD over BC. Okay, in triangle ABD, sinus 30 degrees equals to BD over BC. Sinus 30 degrees is 1/2. Therefore, we'll multiply equation number 1 by BC, and we get that BD equals to BC times sinus 30 degrees, it is 1/2. BC equals to 2 units according to what is given as the question. And we get that BD equals to BC, that is 2 units, times 1/2. 2 over 2 is 1. So in conclusion, we found out that according to equation number 1, BD equals to 1 unit. And BD equals to 1 unit. We continue to focus on triangle ABD. In triangle ABD, cosine 30 degrees equals to DC over BC. Okay. In triangle ABD, the right triangle ABD, cosine 30 degrees equals to DC over BC. Cosine 30 degrees is square root of 3 over 2, and it is equal to DC over BC, and BC is 2. So here we will multiply this equation by 2, and we get that DC equals to square root of 3 units. DC equals to square root of 3 units. So we can write here that DC equals to square root of 3 units. And here we will focus on triangle ADC. In triangle ADC, as it is true in any triangle, the sum of the angles must be equal to 180 degrees. So which angles we have in triangle ADC? We have this angle that is equal to 90 degrees. But before that, we know that angle ACB equals to 75 degrees, and angle DCB is equal to 30 degrees. And the size of angle ACD, the size of this angle ACD, is equal to angle ACB minus angle DCB. I repeat again, the size of the missing angle equals to angle ACD minus angle ACB. Angle ACB equals to 75 degrees minus angle DCB that is equal to 30 degrees. 30 degrees minus 75 degrees equals to 45 degrees. So I found out that this angle equals to 45 degrees, angle DCB equals to 45 degrees. Now we'll focus on triangle ACD. As I already mentioned before, the sum of the angles in triangle ACD must be equal to 180 degrees. So which angles we have in triangle ACD? We have this angle that is equal to 45 degrees plus this angle that is equal to 90 degrees plus this angle that we define as angle X. In total, the sum of those three angles must be equal to 180 degrees. I'll repeat again. The sum of the angles in triangle ACD equals to 180 degrees. So here we will subtract 45 degrees plus 90 degrees is 135 degrees. So 135 degrees plus angle X, in total they must be equal to 180 degrees. So here we'll subtract 135 degrees from this equation, and we get that the missing angle X equals to 180 degrees minus 135 degrees. It is equal to 45 degrees. So this angle X equals to 45 degrees. In the next step, I will copy triangle ACD in a new page and we will analyze triangle ACD. So this is triangle ACD that I copied from the original drawing. Here in triangle ACD, those two angles are equal to each other, and we have the rule that in front of equal angles in the triangle there are equal sides. So here in front of this angle we have side DC, and in front of this angle we have side AD. Okay, so, and according to the rule that I mentioned, the side DC must be equal to side AD, but we already found out that DC equals to square root of 3 units, so we can write here that DC equals to square root of 3 units, and from this equation square root of 3 equals to DC equals to AD, we will derive that AD is also equals to square root of 3 units. So I actually found out that AD equals to square root of 3 units. We can write here that AD equals to square root of 3 units. In the next step, we'll focus on the right triangle, triangle ADC. I'll copy triangle ADC in this page, and we will actually implement the Pythagoras theorem of the right triangle, triangle ADC. So this is the right triangle, triangle ADC that I copied from the original drawing. So according to the Pythagoras theorem, by PT is a relation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is AC, therefore the square of the hypotenuse is AC squared, and it must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to AD squared plus DC squared. Okay, so equation number 1 is the implementation of the Pythagoras theorem on the right triangle, triangle ADC. So we get that according to equation number 1, AC squared equals to AD squared. Here AD equals to square root of 3 units. Therefore AD squared is square root of 3 squared, that is 3, plus DC squared. DC also equals to square root of 3 units, therefore DC squared is square root of 3 squared, that is 3. So in conclusion, we found out that AC squared equals to 3 plus 3, that is 6. Here we take a root out of this equation, equation number 1, and we get that AC equals to square root of 6 units. Now AC equals to square root of 6 units. So actually we found out all the sides of triangle ABC. And we have a formula that gives us the radius of any triangle that blocks a circle. Okay, or the radius of any circle that is inscribed by a triangle, the radius of any circle that is inscribed by a triangle is equal to the area of the triangle, in this case is the area of triangle ABC, over the semi-perimeter of the triangle that blocks the circle. So here, therefore, the radius that we are looking for, here we have triangle ABC that blocks the circle, and therefore the radius of the circle that is inscribed by triangle ABC R will be equal to the area of triangle ABC over the semi-perimeter of triangle ABC. So what is the area of triangle ABC? The area of triangle ABC is equal to the base of the triangle times the height to the base over 2. Okay, again, the area of any triangle, and especially triangle ABC, equals to the base of the triangle times the height to the base over 2. Therefore, the area of triangle ABC will be equal to the base of the triangle. We'll take the base of triangle ABC as AB times the height to the base. The height must create 90 degrees with the base, and indeed DC creates 90 degrees with the base AB, so it is the height is DC over 2. I'll repeat again, the area of triangle ABC is equal to the base of triangle ABC, that is AB, times the height to the base, that is DC over 2. Okay, so the area of triangle ABC is equal to the base of the triangle ABC, that is AD, that is AB, and AB equals to square root of 3 plus 1 times the height to the base, that is DC, that is equal to square root of 3 over 2. So in conclusion, I found out that the area of triangle ABC equals to square root of 3 plus 1 times square root of 3 over 2. Here we'll open the brackets in this equation, and we get that the area of triangle ABC is equal to square root of 3 times square root of 3 is 3, and square root of 3 times 1 is square root of 3 over 2. And repeat again that the area of triangle ABC equals to square root of 3 plus 3 over 2. So here, the area of triangle ABC equals to square root of 3 square root of 3 is 1.732 plus 3 over 2. So the area of triangle ABC equals to here we have 4.3 plus 1.732, it is equal to 4.732 over 2. So in conclusion, the area of triangle ABC is equal to 2.366. And again, the area of triangle ABC equals to 2.366. And what is the semi-perimeter of triangle ABC? The semi-perimeter of any triangle is equal to the perimeter over 2. So here, the semi-perimeter of triangle ABC will be equal to the sum of its sides, the sum of the lengths of its sides, that is actually AB plus AC plus BC over 2. Repeat again, the semi-perimeter of triangle ABC equals to the perimeter of triangle ABC, that is the sum of its sides, over 2. Okay, so here S equals to AB equals to square root of 3 plus 1 plus AC equals to square root of 6 plus BC equals to 2 units, all divided by 2. So S equals to, in conclusion, S equals to, here we have square root of 6 plus square root of 3 plus 3 over 2. So actually we found out that X is equal to square root of 6 plus square root of 3 plus 3. So in the numerator we have 7.1815 over 2 is equal to 3.5907. So here I found out that S equals to 3.5907. The area of triangle ABC equals to 2.366, and the radius of the circle that is inscribed by triangle ABC equals to the area of triangle ABC over the semi-perimeter of triangle ABC. So here we have already found out that the area of triangle ABC equals to 2.366 over the semi-perimeter, that is equal to 3.5907, and it is equal to 0.6589 units. I repeat again, we actually found out that the radius of the circle, the radius of this circle that is inscribed by triangle ABC equals to 0.658 units. So I actually finished the first method. In the next step, I'll present you the second method to find out the area of the circle that is inscribed by triangle ABC. In the second method, we will define the center of the circle as point O. We will define the point of tendency of tangent BC with this circle as point D. We join points O and D together by a straight line. Point D is the point of tendency. Of tangent BC with this circle. So point O is the center of the circle. Point D is a point on the circle itself, and that is exactly the definition of a radius. So we define the radius of this circle as R. So we have here the radius that is drawn to the point of tendency, and here we have rule number 1 that states that a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So here the radius OM is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent AB with this circle, and whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees, according to this rule number 1. So here we have the radius OD that is drawn to the point of tendency, that is to say it is drawn to point D, that is the point of tendency of tangent BC with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius DO. So if BC is perpendicular to DO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. We will join points O and C together by a straight line. We join points O and B together by a straight line. We will define the point of tendency of tangent AB with this circle as point E. We will join points O and D together by a straight line. Point O is the center of the circle. Point E is the point of the circle itself. This is exactly the definition of radius. Therefore, OE is the radius of this circle. E is the point of tendency. Point of tendency of tangent AB in this circle. So here we have the radius OE that is drawn to the point of tendency, that is to say it is drawn to point E, that is the point of tendency of tangent AB in this circle. And whenever we have radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius EO. So if AB is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also will be equal to 90 degrees according to rule number 1. Likewise, we define the point of tendency of tangent AC with this circle SF. Then we join points O and F together by a straight line. Again, point O is the center of the circle. Point F is the point of the circle itself. Therefore, OF is the radius of this circle that is equal to R. So F is the point of tendency of tangent AC with this circle. And again, we have the radius OF that is drawn to the point of tendency. And whenever you have a radius that is drawn to the point of tendency, then tangent AC will be perpendicular to the radius FO. So if AC is perpendicular to FO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. So here we have the external point B. From the external point B, we have two tangents to this circle. We have tangent BE and tangent BD. And according to rule number 2, the lengths of two tangents from a common external point to a circle are equal. So here we have the common external point B. From the common external point B, we have tangent PA and tangent PB, and according to rule number 2, the lengths of those two tangents are equal to each other. That is to say, PA equals to PB. We can implement rule number 2 in our drawing. We have the external point B. From the common external point B, we have tangent BE and tangent BD. And according to rule number 2, the lengths of those two tangents must be equal to each other. That is to say, BE must be equal to BD. Okay? And likewise, if we focus on the common external point C, from the common external point C, we have tangent CF and tangent CD. And according to rule number 2, the lengths of those two tangents must be equal to each other. So CF is equal to CD. Okay, so in the next step we will prove that the green triangle VOD is congruent to the orange triangle BOE. So why those two triangles congruent to each other? So I write it down. Here we have the green triangle that is actually triangle BOD, and the orange triangle BOE. Why the green triangle is congruent to the orange triangle? First of all, we just right now proved that side BD equals to side BE, according to rule number 2. BD equals to BE, and we also know that OD equals to OE, and they are both the radii of the circle, therefore they are equal to each other. Okay, so here side OD equals to side OE, they are both the radii of the circle, therefore they are equal to each other. And finally, we have BO is a common side that belongs to both triangles, so BO equals to itself is a common side that belongs to both triangles. So actually, we proved that the two triangles can go into each other according to side rule. So I write it down. The green triangle that is actually triangle BOD is congruent to the orange triangle BOF according to side rule. And from the fact that those two triangles can go into each other, we'll conclude that the two corresponding angles are also equal to each other. So here we conclude from the fact that the green triangles can go into the orange triangle that angle OBD is equal to this angle OBE, according to the rule that corresponding sides in congruent triangles are equal to each other. Those two angles are equal to each other. So if one angle is alpha, then the other angle must be also equal to alpha. So you can write down that alpha plus alpha, in total the sum of those two angles must be equal to 60 degrees according to what is given as the equation. So alpha plus alpha equals to 60 degrees, that is to say 2 alpha equals to 60 degrees. 2 alpha equals to 60 degrees. We divide this equation by 2 and we get that alpha equals to 30 degrees. So actually we found out that this angle equals to 30 degrees and this angle also equals to 30 degrees. Likewise, we will repeat on the same process on the yellow triangle DOC, and on the pink triangle OFC. First of all, we prove that those two triangles can go into each other according to side rule. The yellow triangle is triangle ODC, and it is actually congruent to the pink triangle OFC. So why the two triangles can go into each other? First of all, we already found out that CF equals to DC. In addition, we know that OF is equal to OD, and they are both the radii of this circle that is equal to R. Repeat again, OF equals to OD equals to R, and finally side OC is a common side that belongs to both triangles, so OC equals to itself. It's a common side that belongs to both triangles. Therefore, we actually proved that the yellow triangle ODC is congruent to the pink triangle OFC. It's congruent to the orange triangle OFC according to side rule. And for the fact that the yellow triangle is congruent to the orange triangle, to the pink triangle, triangle OCF, we will derive that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore those two corresponding angles must be also equal to each other. So here, angle FCO is equal to this angle that is actually angle OCD, and okay, I repeat again, from the fact that the two triangles congruent to each other, we derive that angle FCO equals to angle OCD. So if we define angle OCD as theta, then from this equation we can derive that angle FCO is also equals to theta. So both those two angles are equal to theta, and we know it is given as the equation that theta plus theta equals to 75 degrees. That is to say 2 theta equals to 75 degrees. We divide this equation by 2 and we get that theta equals to 37.5 degrees. So we know that each angle here equals to 37.5 degrees. So here, in the next step, we'll focus on the green triangle. Triangle OBD. In the right green triangle, triangle OBD, we know that tangents 30 degrees equals to OD over BD. Okay, I repeat again, in the green triangle, triangle OBD, tangents 30 degrees equals to OD over BD. So here OD equals to R, so we substitute OD by R, so we get that tangents 30 degrees equals to R over BD. Here, tangents 30 degrees equals to R over BD. So here we multiply equation number 1 by BD, and then we divide it by tangents 30 degrees, and we get that BD equals to R over tangents 30 degrees. So I found out that BD equals to R over tangents 30 degrees. In the next step, we'll focus on the yellow right triangle, triangle ODC. In the right yellow triangle, triangle ODC, it is very easy to see from the drawing that tangents 37.5 degrees is equal to OD over DC. I'll repeat again. In the yellow triangle, triangle ODC, tangents 37.5 degrees equals to OD over DC. Here we'll multiply equation number 2 by DC, and then we will divide it by tangents 37.5 by tangents 37.5 degrees, and we get that DC, according to equation number 2, equals to OD over tangents 37.5 degrees. Okay, OD equals to, this equals to OD over tangents 37.5 degrees. Here OD equals to R, so we substitute OD by R, and we get that this equals to R over tangents 37.5 degrees. Okay, but according to what is given as the question, BC, that is equal to 2 units, it is equal to BD plus DC. BD plus DC. Here, BC equals to BD plus DC. So here BC equals to BD plus DC. So we substitute BD by R over tangents 30 degrees, and we substitute DC by R over tangents 37.5 degrees, and we'll get that here 2 equals to BD equals to R over tangents 30 degrees plus DC, that is equal to R over tangents 37.5 degrees. So we have this equation. Here we'll take R as a common factor out of those two expressions, and we'll get that 2 equals to R. So what is left from this equation after number 2 from it R is a common factor? What is left is 1 over tangents 30 degrees plus what is left from this expression after 2 from it R is a common factor. What is left is 1 over tangents 37.5 degrees. So we got here that 2 equals to R, and tangents 30 degrees is equal to 0.577, and 1 over tangents 30 degrees is equal to 1.73205 plus 1 over tangents 37.5 degrees. So tangents 37.5 degrees is equal to 0.767, and 1 over 0.767 is equal to 1.303. So we found out that 2 equals to R, and 0.303 plus 1.7205 is equal to 1.73205 plus 1.303 03 is equal to 3.03305. So I found out that the radius of the circle equals to R equals to 2 over 303,305, and it is actually equals to 0.6589 units. Okay, so in both methods we found out that the radius of this circle that is inscribed by triangle ABC equals to 0.658 units. So we finished with the first question. In the next step I present to you the second question, and we'll solve the second question in two different methods. Okay, so here in the drawing we have rectangle ABCD. Inside the rectangle we have the circle that is blocked by the rectangle. We know that chord PS equals to 6 units, line segment SQ equals to 5 units, and our mission is to find out the radius of this circle that is blocked by rectangle ABCD. So we'll start with the first method. In the first method, we define the center of this circle as O. Here, point O is the center of the circle. We join points P and O together by a straight line. So point P is a point of tendency. Of tangent BC with this circle. So point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of this circle, so we define the radius of the circle as R. And again we have the radius OP that is drawn to the point of tendency, that is to say it is drawn to point P, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius PO. So if BC is perpendicular to PO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. Okay, and because of the fact that ABCD is a rectangle, we know that all the angles inside a rectangle are right angles, so they are equal to 90 degrees. So here, this angle equals to 90 degrees, this angle also equals to 90 degrees, this angle equals to 90 degrees, and this angle also equals to 90 degrees. we'll define side AB as A. AB equals to A according to our definition. We define side BC, the width of rectangle ABC, as B. BC equals to B, and it is very easy to prove that BC is the diameter of the circle. So we can write here that BC is the diameter of the circle. So if BC is the diameter, it means that the radius must be equal to the diameter over 2, that is B over 2. Okay? And we actually have here a new rule. According to the new rule states that if you draw from the center of the circle perpendicular to any chord, then that perpendicular bisects the chord. So here we have chord SP. We draw perpendicular on chord SP. So here this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and SP as E. According to the rule that I mentioned, the perpendicular OE bisects SP. That is to say, if SE equals to X, then EP also equals to X because of the fact that it divides SP into two equal parts. So if one part equals to X, then the other part also it must be equal to X. So here we'll get that X plus X equals to SP. X plus X equals to SP. X plus X equals to SP. But according to what is given us the question, SP equals to 6. So here we get that X plus X, that is 2X equals to 6. We divide this equation by 2 and we get that X equals to 3 units. Here X equals to 3 units. So here X equals to 3 units and X equals to 3 units. Okay. So here we define the point of tendency of tangent DC with this circle as point F. We will join points O and F together by a straight line. And F is the point of tendency of tangent DC with this circle. Point O is the center of the circle. Point F is the point of the circle itself, therefore OF is the radius of this circle, that is equal to R. And we have the radius OF that is drawn to the point of tendency, and whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius FO according to rule number 1. So if DC is perpendicular to FO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule number 1. So here we created quadrilateral OPFC. Inside quadrilateral OPFC, we have 1, 2, 3 right angles. And when you have a quadrilateral the three right angles, the fourth angle must be also a right angle, so this angle must be also a right angle. Okay, so actually quadrilateral EPFC is a rectangle because it has four right angles. In the next step, from point Q, we will draw perpendicular on BC. I repeat again, from point Q, we'll draw perpendicular on BC. So here, this angle equals to 90 degrees according to our construction. This angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point Q and BC as S. And here, actually, we created, here we define the intersection point of QS with QF as L. So here we created quadrilateral OPLS. Inside quadrilateral OPLS we have 1, 2, 3 right angles. And whenever you have quadrilateral that with 3 right angles, then the fourth angle must be also equal to 90 degrees. So this angle must be also equal to 90 degrees. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So we have here quadrilateral QPLS with 4 right angles, and we also know that the opposite sides of a rectangle are parallel to each other. So here we have rectangle OPLS. This rectangle in rectangle OPLS, its opposite sides are parallel to each other. It means that OP is parallel to LS. Okay, OP is parallel to LS. According to the rule that the opposite sides of a rectangle are parallel to each other. Okay. OPLS is a rectangle. And according to the rule that the opposite sides of a rectangle are parallel to each other, we get that OP is parallel to LS. But LS is part of QS. LS is part of QS. And what is QS? QS is perpendicular from point Q on BC. So QS is a perpendicular, it is absolutely a straight line. QS is a straight line because it is a perpendicular. QS is a straight line. Okay, QS is a straight line. Okay. So QS is a straight line, and part of the straight line QS is parallel to OP. And if part of a straight line is parallel to another straight line, it means that the straight line itself must be also parallel to the other straight line. Here, LS is parallel to OP, therefore the straight line QS must be also parallel to OP. Okay, so we can write down that QS is parallel to OP. QS is parallel to OP. Okay, QS is parallel to OP. And we have the rule that alternating angles between parallel lines are equal to each other. So So those two angles that are located between, those two alternating angles that are located between the parallel lines OP and QS must be equal to each other. So here angle angle SQP, this angle must be equal to this angle that is actually angle OPQ. And if we define one angle as theta, then the other angle must be also equal to theta because of the fact that they are equal to each other. So if this angle is theta, then this angle must be also equal to theta because of the fact that those two angles are equal to each other. Okay? In the next step, we'll focus on quadrilateral QSDC. In quadrilateral QSDC, inside quadrilateral QSDC, we have 1, 2, 3 right angles. And whenever we have 3 right angles inside the quadrilateral, the fourth angle must be also a right angle. So this angle, the missing angle, is also a right angle. So we actually found out that inside quadrilateral QSDC we have 4 right angles, and any quadrilateral that has 4 right angles must be a rectangle. A rectangle is not a square, so we relate to quadrilateral QDSC as a rectangle. Quadrilateral QSDC is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. So a rectangle QDSC, QS must be equal to DC. QS equals to DC. QS equals to DC according to the rule that the opposite sides of a rectangle are equal to each other. But we know that ABCD is a rectangle. So the opposite sides of rectangle ABCD must be equal to each other. That is to say, side DC equals to side AB. DC equals to AB. Okay, DC equals to AB according to the rule that the opposite sides of rectangle ABCD are equal to each other. So from this equation, we will derive that QS is also equal to AB. QS is also equal to AB. And according to our definition, AB equals to A. So we can write it that AB equals to A. Yeah, AB equals to A according to our definition. And from this equation, we'll derive that QS is also equals to A. QS equals to A. QS equals to A. So here we can write down that QS equals to A. In the next step, we will focus on the right triangle OEP. So I'll copy the right triangle OEP. We'll focus on the green right triangle OPE. So I'll copy triangle OPE in a new page, and we'll analyze triangle OEP. So actually we have this angle is 90 degrees, so here we have PE. Here side EP equals to X, that is equal to 3 units. Side OP equals to B over 2. And this angle equals to theta. So actually, this is the right triangle, triangle OEP that I copied from the original drawing. In the right triangle, triangle OEP, we get that cosine theta equals to EP over OP. Cosine theta equals to EP over OP. And EP equals to 3 units. And OP equals to B over 2. So we'll substitute OP by B over 2. Here we'll move 2 to the numerator and B to the denominator, and we get that 2 times 3 is 6 over B. So in conclusion, we found out that according to equation number 1, cosine theta equals to 6 over B. Okay, cosine theta equals to 6 over B. In the next step, we'll focus on the big right triangle, triangle PSQ. In the big right triangle, triangle PSQ, cosine theta equals to, in this right big triangle QSP, cosine theta equals to QS over QP. Repeat again, in the right big triangle, triangle PSQ, cosine theta equals to QS over QP. So here QS equals to A, so we substitute QS by A. What is the value of QP? QP equals to 5 plus 6, that is 11. So in conclusion, we found out that according to equation number 2, cosine theta equals to A over 11. So we actually have two different expressions for cosine theta, therefore we'll create equation number 3 that states that cosine theta according to equation number 1 must be equal to cosine theta according to equation number 2. Okay, so here cosine theta according to equation number 1 is equal to 6 over B, and it must be equal to cosine theta according to equation number 2, that is equal to A over 11. So here we'll multiply this equation, equation number 3, and we'll get that according to equation number 3, A times B equals to 6 times 11 is 66. So we found out that A times B equals to 66. according to our definition, AB equals to A and BC equals to B. And the area of any rectangle is equal to the length of the rectangle, that is AB, times the width of the rectangle, that is BC. I repeat again, the area of rectangle ABCD will be equal to the length of the rectangle, that is AB, times the width, that is BC. So AB equals to A, according to our definition, and BC equals to B, according to our definition. Therefore, we found out that the area of rectangle ABCD equals to A times B. We just right now found out that A times B is 66. So in conclusion, we found out that the area of rectangle ABCD is equal to 66 square units. Okay, so we actually finished with the first method. In the next step, I will present to you how to find out the radius of this rectangle, the area of this rectangle ABCD, according to the second method. Okay. In the second method, we define, first of all, we know that all the angles inside a rectangle are right angles, therefore this angle equals to 90 degrees, this angle equals to 90 degrees. This angle also equals to 90 degrees. And finally, this angle, it is also equals to 90 degrees. Okay. We will define the center of this circle's point O. We join points O and P together by a straight line. Point P is the point of tendency. Of tangent BC with this circle. And again, point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of this circle. We define AB as A, as we did in the first method. And we define BC as B. BC is also the diameter of the circle. So if BC is the diameter that is equal to B, it means that the radius equals to B over 2. Again, we have the radius OP that is drawn to the point of tendency. Therefore, according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. In the next step, we will extend the radius PO until it intersects with the side of the rectangle. So here we define the intersection point of the extended radius PO and AD as point F. So inside quadrangle ABPF we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. And here inside quadrangle FPCD we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. So here we know that the opposite sides, here we have in quadrangle ABFP we have 4 right angles, and any quadrangle that has 4 right angles must be at least a rectangle, if not a square. So we relate to quadrangle ABPF as a rectangle, and we know that the opposite sides of a rectangle are equal to each other. So AB equals to FP, but according to our definition, AB equals to A, and it is also equals to FP, according to the rule that the opposite sides of a rectangle are equal to each other. Therefore, FP must be also equal to A. We will define this point as point L. We join points L and S together by a straight line. What is the definition of line segment LP? PO is the radius. So line segment PO passes through the center, that is point O, and that is the circle point L. So we have chord LP. Chord LP passes through the center of the circle, that is point O. Any chord that passes through the center of the circle must be the diameter of the circle. So here LP is the diameter of the circle. And we have already found out that the diameter of the circle is equal to B. So here we have peripheral angle LSP that rests on the diameter of the circle, that is LP. And we have rule that states that any peripheral angle that rests on the diameter of the circle must be a straight line. So this peripheral angle LSP that rests on the diameter of the circle, that is LP, must be equal to 90 degrees. Okay. So in the next step we'll prove that the right triangle LSP is similar to the big right triangle QFP. But before that, we define angle LPS as theta. So if angle LPS equals to theta, so this angle equals to theta. This angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta, because of the fact that 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. Likewise, exactly for the same reason, if we focus on triangle QFP, this angle equals to theta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees according to the same rule. Okay, in the next step we'll prove that the green triangle LSP is similar to the big triangle, to the big right triangle QFP. Okay, so here we have triangle QFP, the big right triangle, and the right green triangle LSP. So why those two triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So here angle QFP in the big right triangle is equal to angle LSP in the green right triangle, SLP. And they are both equal to 90 degrees, therefore they are equal to each other. I'll repeat again. Angle QFP, it is actually angle QFP in the big right triangle is equal to angle all FP or to angle LSP is equal to angle SLP is equal to angle SLP. Again, angle QFP in the big right triangle is equal to angle SLP in the green right triangle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So this angle, that is actual angle FQP, is equal to this angle, that is actual angle SLP, they are both equal to 90 degrees minus theta, therefore they are equal to each other. I repeat again. Angle FQP in the big right triangle equals to angle SLP in the small green triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. And finally, this angle, angle theta, is a common angle that belongs to both triangles, therefore the angle equals to itself. Or we can also write down that we can call angle theta in two different names. Angle theta is equal to angle QPF, and it is equal to itself. We can call angle theta as angle SPL. Repeat again. Angle theta equals to itself. It's a common angle. Angle theta, that is angle QPF, equals to angle SPL equals to theta. Okay, so here we actually found out that the big right triangle QFP is similar to the green right triangle SLP according to angle similarity rule. Okay. Repeat again, the green small right triangle SLP is similar to the big right triangle QPF according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that here PF, that is the side of the big right triangle, over SP, that is one side of triangle, the small green triangle SPL, over SP is equal to QP over PL. Repeat again, from the fact that the green small right triangle is similar to the big right triangle, we conclude that PF over SP equals to QP over PL. So here PF equals to A according to what we already found out, so we substitute PF by A over SP. SP equals to 6 according to what is given as the question, so we substitute SP by 6 and it is equal to QP. QP equals to 5 plus 6, that is 11, so we substitute QP by 11 over PL. PL is the diameter of the circle, that is equal to B. So in conclusion, we found out that according to equation number 1, A over 6 equals to 11 over B. Here we cross multiply this equation number 1, and we will get that A times B equals to 6 times 11, that is 66. So AB equals to 66, and we know that the area of a rectangle, and especially rectangle ABCD, equals to the length of the rectangle, that is AB, times the width, that is BC. The length times the width is the area of triangle ABCD. The AB equals to A according to our definition, BC equals to B according to our definition. So in conclusion, we found out that the area of triangle ABCD equals to A times B, and we just right now found out that A times B equals to 66. So in conclusion, we found out that the area of triangle ABCD equals to 66 square units. 66 square units. So in both methods, we found out that the area of a rectangle ABCD equals to 66 square units. We finish with the second method. In the next step, I will summarize the lecture. Okay, let's start with the first question. So in the drawing we have triangle ABCD. Inside triangle in the drawing we have triangle ABCD. Okay. In the drawing we have triangle ABC. Inside this triangle ABC we have a circle that is inscribed by triangle ABC. This angle equals to 60 degrees, this angle equals to 75 degrees. And we also know that side BC equals to 2 units. And our mission is to find out the radius of this circle that is described by triangle ABC. So in the first step, this is the first method. in the first step from point C, we draw perpendicular on AB. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. Then we focused on the right triangle CBD. In the right triangle CBD, we know that the sum of the angles of triangle CBD is equal to 180 degrees. So we have this angle that is equal to 90 degrees, this angle that is equal to 60 degrees, plus this missing angle that is x. So here 60 degrees plus 90 degrees plus x must be equal to 180 degrees according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So 60 plus 90 is 150, so 150 plus x equals to 180. We subtracted 150 from this equation and found out that x equals to 30 degrees. This angle equals to 30 degrees, so we continue to focus on the right triangle CBD. The right triangle CBD since 30 degrees equals to BD over DC. Since 30 degrees equals to BD over DC. We multiply this equation number 1 by BC and found out that BD equals to BC times sinus 30 degrees and sinus 30 degrees is 1/2. So in conclusion, we found out that BD equals to BC times 1/2 and BC equals to 2 units according to what is given as a question. So we substituted BC by 2 and found out that BD equals to 2 over 2, that is 1. So we found out that BD equals to 1 unit. Then we continue to focus on the right triangle BCD. The right triangle BCD, we know that cosine 30 degrees equals to DC over BC. So here we multiplied this equation by BC and found out that here cosine 30 degrees is equal to 3 over 2, that is equal to DC over BC, and BC equals to 2, so we substitute BC by 2 and we got that square root of 3 over 2 equals to DC over 2. We multiply this equation by 2 and found out that DC equals to square root of 3 units. DC equals to square root of 3 units. Okay? Then we focus on triangle ADC. In triangle ADC, what is the size of this angle? It is very simple to see from the domain that this angle ACD equals to angle ACB, that is 75 degrees, minus angle DCB, that is 30 degrees. 75 degrees minus 30 degrees is 45 degrees, so we found out that this angle equals to 45 degrees. Then so this angle equals to 45 degrees, this angle equals to 90 degrees, and the sum of the angles in triangle ADC is 180 degrees. So in triangle ADC, 45 degrees plus 90 degrees plus the missing angle x, in total it must be equal to 180 degrees. 45 degrees plus 90 degrees is 145 degrees. So we found out that 145 degrees plus x equals to 180 degrees. Here we subtracted 145 degrees from this equation and found out that the missing angle equals to 45 degrees. So I copied the right triangle ADC in this new page and we analyze triangle ACD. In triangle ACD, those two angles are equal to each other. They are both equal to 45 degrees, therefore they are equal to each other, and we have the rule that in front of equal angles in the triangle there are equal sides. So here, in front of this side, in front of this angle we have side DC, in front of this angle we have side AD. DC must be equal to AD, according to the rule that I mentioned. But here, DC equals to square root of 3 units. So from this equation, square root of 3 equals to DC equals to AD. We derive that AD is also equals to square root of 3 units. So here, AD is also equals to square root of 3 units. Okay? So actually we found out all the sides of triangle ABC, and we have a special formula for the radius of any circle that is described by a triangle. The radius of a circle that is described by a triangle equals to the area of the triangle that blocks the circle over the semi-perimeter of the triangle that blocks the circle. So in this case we are talking about triangle ABC. The area of triangle ABC equals to the base of the triangle times the height to the base over 2. The base is AB, the height to the base is DC over 2. So AB times DC over 2 is the area of triangle ABC. AB equals to square root of 3 plus 1. DC equals to square root of 3. And when we divide it by 2, we get that the area of triangle ABC equals to square root of 3 plus 1 times square root of 3 over 2. So in conclusion, we found out that the area of triangle ABC equals to 2.366 square units, and the semi-perimeter of any triangle equals to the perimeter over 2. That is to say, triangle ABC is AB times plus AC plus BC over 2, and the result is that the semi-perimeter of triangle ABC is equal to 3.3907. The area of triangle ABC is 2.366. Therefore, the radius is equal to the area of the semi-perimeter, and found out that the radius equals to 0.6589 units. We finished with the first method. Then I presented to you how to find out the area, how to find out the radius of this circle that is described by triangle ABC according to the second method. In the second method, we used rule number 1, that the tangent to a circle is perpendicular to the radius drawn to its point of tangency, and also rule number 2, that the lengths of two tangents from a common external point to a circle are equal. Therefore, we actually proved that the orange triangle is congruent to the green triangle according to side rule. Therefore, those two angles must be equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So if one angle is 30 degrees, then the other angle must be also equal to 30 degrees. Those two triangles are also congruent to each other according to side rule. Angle ACB equals to, in total, to 75 degrees, so each angle must be equal to half of it, that is 37.5 degrees. Then we found out that according to the rule that triangles 30 degrees equals to OD over BD, we found out that BD equals to R over triangles 30 degrees, and here also we have triangles 37.5 equals to OD over DC. Therefore, DC equals to R over triangles 37.5 degrees, and BC equals to BD plus DC. That is to say, BC is equal to 2 units equals to BD plus DC. This is the value of BD, this is the value of this is the value of BD, this is the value of DC. We have only one variable that is missing here, that is R. So we put on the values of triangles 30 degrees and triangles 37.5 degrees, and found out that the radius of this circle that is described by triangle ABC is equal to 0.658 units. So we finished the first question. Then I presented to you the second question, and we solved the second question in two different methods. In the first method, so we have to find out the area of this rectangle. In the first method, we used the rule that if you draw from the center of the circle perpendicular on any chord, it bisects the chord. So here we draw perpendicular on SP, so it bisects the chord SP, that is to say, here SE equals to SP, and because of the fact that SP equals to 6, it means that S equals to 3 units and EP also equals to 3 units. And we also, from point Q, we draw perpendicular on BC. So here we created a triangle. Then in triangle OPLS, OP is parallel to LS. In rectangle OPLS, OP is parallel to LS, therefore OP must be also parallel to QS. And we have the rule that in front, alternating angles between parallel lines are equal to each other, so those two angles are equal to each other. And we have from this right triangle, we found out that cosine theta equals to 6 over b, and from the big right triangle, we found out that cosine theta equals to a over 11. Then we created equation number 3 that states that cosine theta according to equation number 1 must be equal to cosine theta according to equation number 2, and found out that AB, that is the area of rectangle ABCD, is equal to 66 square units. Then, according to the second method, we used actually the rule that those two triangles are similar to each other according to side rule. The green triangle PLS is similar to the big triangle PFQ according to side rule. And because of the fact that the two right triangles are similar to each other, we concluded that PF over SP equals to QP over PL. PF equals to A, SP equals to 6, QP equals to 11, and PL equals to B. So in conclusion, we found out that AB equals to 66 square units. And here, when we extend that PO, we created here rectangle BPAF, and in the opposite sides of rectangle are equal to each other, therefore AB equals to FP. So if AB is A, then FP also must be equal to A. And we also have here peripheral angle LSP that is equal to that is rest on the diameter LP, therefore it must be equal to 90 degrees. Therefore the green triangle is a right triangle, and the triangle QFP is also a right triangle. The two right triangles have a common angle theta. So if this angle is theta, this angle must be equal to 90 degrees minus theta, and this angle must be also equal to 90 degrees minus theta. Therefore, the two right triangles are similar to each other. From the fact that they are similar to each other, we derive this equation, and from this equation we found out that the area of a rectangle ABCD equals to 66 square units. So in both methods, we found out that the area of this triangle ABCD equals to 66 square units. Okay, in the first method we actually used a new rule that whenever you draw from the center of a circle perpendicular to any chord, it bisects the chord. And we also used the rule that alternating angles between parallel lines are equal to each other, while in this method we use the rule that any peripheral angle that rests on the diameter must be equal to 90 degrees, and we proved that the two right triangles are similar to each other, and from this we derive that the area of rectangle ABCD equals to 66 square units. Okay, so in both methods we found out that the area of this rectangle ABCD, it is equal to 66 square units. Okay, thank you very much.